Howdy everyone, welcome to the May update of Science and Force Fields at OpenFF, where I'll summarize some of the progress we've been making over the past month on force field development projects that are part of the OpenFF roadmap. This recording will be shorter than usual. Most of the OpenFF team, and indeed much of OMSF, were away at the Alchemistry and OMSF workshops in Boston a couple weeks ago. So last time I talked about how the SAGE 2.3.0 fit was going, and this will be our first force field with a neural network charge model. Apologies for the deja vu. We've gone back to the drawing board and started the fit again. And the reason for this is that we've discovered problematic data in ThermoML was negatively affecting our 2.3.0 fit, in particular the van der Waals parameters. So specifically, we discovered issues where properties that were measured at high pressure were entered as atmospheric pressure, properties where the mole fractions of components in binary mixtures were swapped, and also issues where molecules were just incorrectly specified. So for example, with esters, swapping in pentyl methanoate instead of methyl pentanoate. These issues were also present in the SAGE 2.0 training set, but when we went back and looked at the fit, the performance didn't seem to be substantially negatively affected by these incorrectly entered properties. So the current status of the SAGE 2.3.0 refit is we've cleaned the ThermoML training set. We've refiltered the training and validation set, and I've checked the training set to ensure that there are no glaring outliers that could be the result of bad data. We've equilibrated those properties, and now we're in the process of refitting the van der Waals terms to the new training set. Based on how long it took last time, we anticipate that we should have this force field ready in a month or so. Separately, we're also in communication with NIST on the ThermoML properties and the issues that we've discovered. So hopefully they can fix those issues in their dataset or in the database and make a clean release. In terms of quantum chemistry datasets that we're currently computing, last time I mentioned that we added a new torsion drive dataset for torsions with low coverage, and this is now complete. A couple of our larger datasets, the transition metal single point set that Jen put in, and the Hessian calculations are still ongoing. And this is all being masterminded by Jennifer Clark, who is also continuing work on our collaboration with Genentech and the Cadera Lab in putting together a diverse data set of transition metal ligand complexes. Moving on to the lipid force field, which is being driven by Julianne in the Schertz lab. Just as a refresher, she started off by benchmarking the performance of our existing force fields on lipid bilayers and pure alkanes. And when using SAGE 2.2.0 on alkanes, we saw that we slightly underestimate densities. We get heats of vaporization, pretty similar to experiment, but we also see much slower diffusion. Last time I mentioned that Julianne had refit SAGE to new alkane and phosphate data, but that didn't substantially change the parameters of the force field or improve their performance. So for example, the alkane torsion profiles, as shown on the right-hand side here, still incorrectly favor the gauche structure over the trans state. Since then, Julianne has refit the force field just to alkanes to see the effect on our benchmark properties. And looking at QM profiles, or at least those of the training set, this winds up reproducing the QM energies near exactly and gets the relative minima of the gauche and trans structures correct. It also affects the physical properties of condensed phase simulations. So it increases the densities and the heats of vaporizations of alkanes to the detriment of the longer chain alkanes, with the result that pentadecane now freezes in simulation at 300 Kelvin. And what's also interesting is that in condensed phase simulations, when comparing the relative populations of alkanes in the trans state and the gauche state, the trans state is now much more favored, overly so, compared to gauche. In simulations of POPC, Julianne is also seeing that the area per lipid is much lower than experiment, although noting that benchmarks are still in progress. So the takeaway here seems to be that just getting the alkanes right when we fit to QM energy profiles in the gas phase doesn't necessarily result in overall better performance in the condensed phase. So in terms of next steps, Julianne is refitting the alkane van der Waals terms to heats of vaporization to see if that improves the performance of the force field on condensed phase properties. Last but not least, Chapin has continued work on the protein force field. So just as some historical context here, Chapin found that simply refitting the force field to protein QM data resulted in force fields where the secondary structure of GB3 unravels in solution, mostly the orange part of the helix shown here. Chapin is now trying an approach where he refits the backbone torsion parameters to NMR observables, and over a series of iterative fits has been seeing much better performance in terms of helix stability. Since last time, another iteration of this process has been completed, resulting in a force field that doesn't show perfect helical stability, but unfolds and refolds GB3 at the C-terminus and in the middle of the helix. And this is quite interesting because this is the first force field where we've seen refolding behavior. Interestingly, it performs worse on sidechain scalar couplings compared to the previous iteration. And Chapin plans to continue iterating on this process to see if behavior improves. Chapin has also been benchmarking other folded proteins beyond GB3, looking at the force field candidates that he's fit so far. He's seen that BPTI and ubiquitin both stay folded, but that hen egg white lysozyme, or HUL, also unfolds in quite a similar manner to GB3, also at the helices. Here as well, performance improves after refitting to the GB3 NMR observables, suggesting that helices in general are being stabilized, not just specifically to GB3. Chapin has also been running additional QM fits to the larger former dataset that Arnica put together. And on initial benchmarks, he has seen that this force field performs similarly on QM benchmarks compared to the other NMR fit force fields, but unfolds the GB3 helix quickly in simulation. In terms of next steps, Chapin plans to continue iterating on the NMR fits, to start working with replica exchange on umbrella sampling for the NMR fitting, to move forward with additional fits to the larger QM dataset by fitting the specific model as well as continuing to benchmark other NMR observables. So that's what's been happening over the past month at OpenFF. Thanks for listening. I'll see you next month.